For months, Earth's most powerful telescopes have been tracking the journey of an interstellar visitor, the mysterious 3I Atlas. Now, that much-discussed moment has arrived. October 29 marks its perihelion, the point closest to the Sun, and with it, the perfect opportunity to observe what many astronomers call the critical instant. This object, which comes from interstellar space, moves at such a high velocity that it traverses our solar system without being captured by the Sun's gravity. But during this close approach, something could change. Scientists hope to record unique data that will help us understand how bodies from outside our system behave. Will it accelerate, will its trajectory deviate, or will it simply continue on its path into the void? The truth is that every second of observation will be essential. Before we continue, do not forget to leave your like and tell me in the comments from which part of the world you are watching this video. From the United States, Mexico, Australia, or perhaps from another country that is also observing the passage of 3I Atlas. Prepare yourself, because on this journey we will explore the most recent data, the scientific hypotheses, and what this historic passage of an object truly represents, one that reminds us how small our place in the cosmos is. Atlas, the third interstellar object detected passing through our solar system, is writing a new chapter in the history of modern astronomy. After Oumuamua and Comet Borisov, this visitor has become the focus of global observations. Since its discovery, astronomers have carefully followed its trajectory using terrestrial and space telescopes like Pan-STARRS and the solar monitoring systems of NASA and ESA. On October 29, 2025, 3I Atlas will reach its closest point to the Sun, the perihelion, at a critical distance to perform what in orbital mechanics is known as a possible Oberth-type maneuver. This effect, theorized by Hermann Oberth, describes how an object can obtain an additional impulse if it modifies its trajectory near a source of great gravity, like the Sun. It is at this point that astronomers hope to observe any subtle change in its speed or direction. Social media is full of theories, from the scientific to the purely imaginative. However, observatories confirm that 3I Atlas represents no danger to Earth. Its close passage will be a historic opportunity to study how interstellar materials interact with solar radiation. In the upcoming sections, we will explore with scientific precision what we know about its approach, why this moment is so important, and how every fragment of light reflected by its surface can reveal secrets about its origin. The 3I Atlas, officially designated as the third interstellar object detected in our solar system, is entering the most delicate phase of its trajectory, the perihelion. In simple terms, the perihelion is the point at which a celestial object passes closest to the Sun during its orbit. But when it comes to a visitor that originates from interstellar space, that point becomes more than just an astronomical coordinate. It is a unique scientific opportunity and also the stage for the boldest theories about the physics of the cosmos. During the last few weeks, observatories all over the world, including Pan-STARRS in Hawaii, the Very Large Telescope in Chile, and the observation network of the Solar and Heliospheric Observatory, have directed their instruments towards the same objective, to record with the greatest possible precision how 3I Atlas behaves as it approaches our star. What is sought is not only to confirm its trajectory, but to detect potential variations in its speed or brightness that might suggest an unusual interaction with solar radiation or the solar wind. The phenomenon known as the Oberth effect comes into play here. This principle, proposed by the pioneer of astronautics, Hermann Oberth, establishes that an object or spacecraft can gain more energy by igniting its propulsion system or altering its direction when it is at the point of maximum orbital velocity, that is to say, near a source of intense gravity. In other words, if an object performs a trajectory change at the precise moment it passes by the Sun, it could obtain a colossal impulse by utilizing the star's gravitational energy. In the case of 3I Atlas, that instant coincides exactly with its passage on October 29. Of course, in this case we are not speaking of an engine or an intentional maneuver, but astronomers are studying whether natural forces, like the outgassing or sublimation of volatile materials, could generate a similar effect. If 3I Atlas contains icy compounds in its interior, the extreme heat of the perihelion could release jets of gas that would act like small natural thrusters, subtly altering its course. A change of just a few millimeters per second could modify its destiny millions of kilometers later. The interesting thing is that this type of phenomenon has already been observed in comets coming from the Kuiper belt and in the case of the interstellar comet Borisov in 2019. However, 3I Atlas is different from all of them. Its elongated shape, its irregular brightness, and its speed suggest an atypical composition. The first spectroscopic analyses indicate the presence of metallic silicates mixed with organic compounds, which reinforces the idea that it is not a classic comet, but rather an interstellar rocky fragment that has survived the journey between stars. Orbital calculations show that 3I Atlas will pass at a distance of approximately 0.37 astronomical units from the Sun, that is to say, about 55 million kilometers. Although that figure seems large, it is close enough for the temperatures on its surface to exceed 600 degrees Celsius, provoking an intense sublimation of any remaining ice or volatile material. At that point, the pressure from the gas and radiation could act upon its surface, generating a detectable non-gravitational acceleration. In scientific terms, this would not only serve to confirm theories about the thermal behavior of interstellar objects, but also to test the limits of orbital mechanics applied to non-periodic bodies. Every variation in its brightness, every minimal deviation from its trajectory recorded by the telescopes, will be analyzed with high-precision computational models. Teams from NASA and ESA have already scheduled simulations on supercomputers to compare the real observations with the theoretical scenarios. For astronomers, this moment represents an opportunity equivalent to having a spacecraft sent from another stellar system passing right before our eyes. It is a natural laboratory to study materials that formed in environments completely distinct from our own. That is why, in the coming days, every photon reflected by 3I Atlas will be measured and its light broken down into spectra to determine which elements compose its surface. However, outside the scientific realm, public attention is also at its peak. On social media, theories circulate ranging from possible dangerous deviations to completely unfounded ideas about its artificial origin. In light of this, the most prestigious observatories have reiterated time and again that the trajectory is perfectly calculated. The 3I Atlas represents no danger to Earth. Its trajectory, although inclined relative to the ecliptic plane, remains stable and will lead it to exit the solar system in the coming months, following a predictable hyperbolic curve. What makes this perihelion so special is the coincidence between the object's extreme velocity, more than 90 km per second, and its passage through the densest region of the solar gravitational field. That combination creates an energetic environment so potent that any detectable variation could become direct proof of the Oberth effect, albeit without human intervention. For scientists of orbital dynamics, seeing something like that is comparable to witnessing a cosmic experiment performed by nature itself. On a historical level, this moment can be compared to the arrival of Oumuamua in 2017, but with a crucial difference. Back then, astronomers barely managed to track it for a few weeks before it disappeared into deep space. In contrast, with 3I Atlas, international teams have been able to coordinate observations from multiple angles, including infrared, optical, and radio telescopes. This will allow for nearly complete coverage of its behavior during the perihelion and its subsequent exit from the solar system. At the Institute of Astrophysics of the Canary Islands, researchers have developed a campaign to compare the apparent brightness of 3I Atlas with solar reflection models used for metallic asteroids. If the data coincides, it could be confirmed that this object is not primarily icy, but rocky, which would explain why it has resisted for so long without fragmenting. But if sudden light variations are detected, then the scenario changes. It would mean that its surface is reacting to the solar heat in an active manner, perhaps releasing gases trapped for millions of years. And while all this is happening, one question guides every observation. Will this be the turning point where 3I Atlas shows an unexpected change? If the models predict its behavior correctly, we will see a slight adjustment in its velocity after October 29. If not, something new will have to be learned about the physics of interstellar travelers. The countdown is already underway. Every passing hour brings 3I Atlas closer to a decisive moment that could reveal more about how bodies that travel between stars move. What happens during this perihelion will not only be one more page in the astronomical records, but a key to understanding the processes that shape the wandering objects of the universe. And as the sun illuminates its surface for the last time, before it moves away into the darkness of space, the world's telescopes are preparing to record every flash, every variation, every signal that can help us understand a little more about our place in the cosmos. From the moment the approach of 3I Atlas to the sun was announced, social media became filled with sensationalist headlines, viral videos, and supposed global alerts claiming that the object could be on a collision course with Earth. These publications, shared millions of times, exploited the public's lack of knowledge about how orbital trajectories are calculated and how official astronomical records work. But science has been clear and forceful. The 3I Atlas represents no danger whatsoever. Its orbit, confirmed by multiple international observatories, follows a hyperbolic trajectory that guarantees its definitive exit from the solar system after the perihelion. The problem is not new. Every time a celestial body approaches the inner solar system, especially when its origin is interstellar, a wave of disinformation surges. Recent history with the object Oumuamua is the most remembered example. The variations in its brightness and its irregular shape gave rise to speculations about a possible alien spacecraft. However, subsequent spectroscopic analyses demonstrated that it was a natural object, although unusual, with behavior explained by known physical effects. The same thing is happening now with 3I Atlas, a mixture of legitimate curiosity and viral disinformation. To understand why scientists dismiss the idea of an impact with Earth, one must review how trajectories are calculated. In astronomy, astronomers determine the position of an object through precise observations of its movement in the sky, which is called astrometry. Each observation provides exact coordinates, right ascension and declination, and when combined, an orbital model is constructed. When a body is observed for weeks or months, the predictions about its path become extremely reliable, especially if its movement shows no anomalies. In the case of 3I Atlas, the data accumulated since its initial detection allowed for the certain determination that its trajectory does not intersect Earth's orbit. The object will pass far above the plane of the ecliptic, moving further away each day after October 29. The calculations were verified by the Minor Planet Center and NASA's Jet Propulsion Laboratory, the bodies responsible for cataloging all objects that approach our system. Simulations performed with supercomputers confirm that there is no possibility of impact, not even in the long term. So, why do rumors continue to circulate? Part of the answer lies in human fascination with the unknown. An object that comes from another stellar system naturally awakens extraordinary theories, but science works with evidence, and so far, all of it points to a completely natural explanation. The variations in the brightness of 3I Atlas are due to its irregular rotation and the way it reflects sunlight, not to any type of technological activity. Another factor fueling misunderstandings is the confusion between astronomical terms. When the media mentions an approach to the sun or entry into the inner solar system, many people interpret it as an imminent threat. In reality, the majority of bodies that cross the solar system do so without representing any risk. Even much larger comets like Halley or Neowise have passed relatively close to the Sun without altering their trajectories or endangering Earth. The difference with 3I Atlas lies in its origin. Coming from outside the solar system, its speed and angle of entry are unusual. Astronomers are precisely interested in that, in how interstellar objects are deflected, accelerated, or slowed down by the gravity of the Sun and the planets. Every measurement helps to improve models of galactic dynamics, to understand how stellar systems exchange material, and to estimate how many fragments like this one could be traveling silently between the stars. The European Space Agency in conjunction with NASA has issued official statements clarifying that the simulations of its trajectory have been corroborated by independent observatories. In fact, one of the most fascinating elements of this object is its exit velocity. After the perihelion, 3I Atlas will reach a speed exceeding 100 km per second, a figure that greatly surpasses the solar system's escape velocity. This means that once it completes its passage, no celestial body will be able to retain it. In other words, 3I Atlas will not stay here, it will continue its interstellar journey, perhaps towards another system millions of years from now. The responsibility of specialized media and science communicators has been crucial in this context. Observation channels like the Virtual Telescope Project and the network of amateur astronomers Skylife have transmitted real-time observations, showing the public how an object of this type is tracked. Thanks to these broadcasts, millions of people were able to see 3I Atlas moving slowly against the backdrop of stars, visually confirming its course. Furthermore, communications from the Solar and Heliospheric Observatory and the James Webb Space Telescope have provided data that dismantles any apocalyptic theory. The infrared images from the James Webb Space Telescope show a thermal signature consistent with mineral and metallic materials, without any kind of artificial energy pattern. In other words, everything observed about 3I Atlas fits within the framework of natural physics. Astronomers emphasize that this type of observation is fundamental not only for debunking myths but for strengthening scientific culture. In an era where any rumor multiplies in seconds, evidence must be the shield against disinformation. In fact, one of the most important achievements of the scientific community in this event has been international collaboration. Observatories in America, Europe, Asia, and Oceania have shared data in real time to guarantee maximum precision in the orbital models. That cooperation has allowed for the detection of even small variations in brightness that help determine the object's rotation and shape. On the other hand, the popular narrative that tries to link every interstellar object with extraterrestrial life does not stop. It is understandable. The idea that something could come from another system awakens our collective imagination. However, scientists insist that the data does not support that hypothesis. The surface of 3I Atlas reflects light irregularly, yes, but that is common in elongated, rotating bodies. Its chemical spectrum shows no signs of manufacturing or artificial structures. What we have before us is a natural piece of cosmic matter shaped by millions of years of interstellar travel. The demystification of 3I Atlas also teaches us something important about the way we interpret the universe. Every time humanity discovers something new, the first reaction is usually divided between awe and fear. But science exists precisely to transform that fear into knowledge. This object, far from being a threat, is a reminder that we live in an open system where fragments from other worlds can visit us and offer us clues about how planets beyond our sun formed. The truth is that 3I Atlas has become a symbol of international collaboration and scientific precision. Every photograph, every spectrum, and every measurement contributes to a data bank that will help us better understand the exchange of matter between stars. And although rumors will continue to appear in every corner of the internet, the truth will remain written in the astronomical records. The orbit of 3I Atlas is calculated. Its passage is safe, and its destiny is inevitably a return to the interstellar void from which it came. Instead of fearing its passage, we should celebrate the opportunity it represents. It is the first time we can observe an interstellar object for so long and with such resolution. October 29th will mark a before and after. Not because something will happen to Earth, but because we will be able to see with data and proof how a traveler from deep space behaves when facing the gravity and heat of the sun. Knowledge, in the end, always conquers fear. Although science has been categorical in stating that 3I Atlas is a natural object, the possibility of it being of technological origin continues to fascinate millions of people. It is not just a modern fantasy. Every time an interstellar visitor is detected, the same question arises: what if it is not a simple rock? This human impulse to seek patterns and purposes in the unknown has accompanied all the great astronomical observations in history. But in this case, the question has special value because 3I Atlas behaves in such a singular way that some find it difficult not to consider an artificial alternative. Since its discovery, astronomers noticed that its brightness varied irregularly, suggesting its shape was extremely elongated, something uncommon in natural bodies. Its aspect ratio, that is, the proportion between its length and width, exceeds that of any known asteroid. This immediately evoked the memory of Oumuamua, whose strange behavior in 2017 triggered global debates. Back then, Professor Avi Loeb from Harvard University publicly proposed that Oumuamua could have been an interstellar probe sent by an advanced civilization. Although his hypothesis was widely discussed and criticized, it raised a crucial point. The universe is immense, and we cannot completely rule out that some objects might have a non-natural origin. The case of 3I Atlas, however, differs in one key aspect. Its physical properties can be explained without resorting to technological hypotheses. Optical and infrared spectra show that its composition is compatible with metallic silicates and carbon compounds, materials common in asteroids and planetary fragments. Furthermore, its speed and trajectory are consistent with the laws of orbital mechanics. But then, why does the idea that it could be something more remain alive? Part of the appeal of this hypothesis comes from the way popular culture has mixed science and mystery. Movies, books, and alternative theories have shaped a narrative where any astronomical anomaly is interpreted as a sign of intelligent life. In a world where technology advances by leaps and bounds, thinking that another civilization could have achieved the same or even more is tempting. However, the data for 3I Atlas is cold and exact. Nothing in its behavior suggests control or intentional direction. Its movement is that of a body responding solely to natural forces, gravity, radiation, and heat. Still, it is worth exploring the hypothetical scenario. If 3I Atlas were a ship or a technological probe, what would its purpose be? From a logical point of view, approaching the Sun could make sense if the goal were to take advantage of a gravitational maneuver, a slingshot, to change direction and accelerate towards another destination. In terms of engineering, this maneuver is the most efficient way to gain energy using the gravitational impulse of a star. However, if that were the case, observation instruments would have already detected some type of energy emission or a controlled change in acceleration, and that has not occurred. Furthermore, if an advanced civilization truly wanted to study or intervene on Earth, doing so in a visible manner would be illogical. From a strategic point of view, an attack or open contact would be the least efficient option. Any civilization capable of traversing interstellar space would understand the laws of energy conservation and the risks of exposure. Moreover, the basic principle of cosmic survival indicates that an advanced species would avoid conflicts with other emerging civilizations. Therefore, the idea of an attack or invasion lacks logical, scientific, and energetic foundation. On the other hand, there exists the possibility, more philosophical than technological, that ancient civilizations sent unmanned probes, similar to the messages that humanity has launched into space, like the Voyager or Pioneer probes. If 3I Atlas were something similar, its design should be detectable by the electromagnetic emissions it would produce when interacting with solar radiation. The radio telescopes of the SETI project and the Allen Telescope Array monitored the object for weeks seeking radio signals or coherent pulses, without results. The records show only natural noise without any frequency indicating artificial transmission. The scientific conclusion is clear. There is no evidence supporting a technological origin. But beyond that, the popular interest in the alien hypothesis reveals something profound about human psychology. When we observe something we do not completely understand, we seek meaning. We cannot bear the vacuum of the unexplained. That is why 3I Atlas is not only an astronomical phenomenon but also a mirror of our need to find companionship in the cosmos. Interestingly, this fascination has had a positive effect. It has brought millions of people closer to astronomy. Searches related to 3I Atlas multiplied on science communication portals, and many young people began following live observatory streams for the first time. In a way, the mystery, although unfounded, has served as a gateway to knowledge. Scientists, aware of this, do not disdain the public's questions. On the contrary, they use them as an opportunity to explain natural processes in an accessible way. The main message is that the universe is sufficiently surprising without the need to adorn it with fiction. The mere existence of an object traveling between stars, crossing the vastness of space for millions of years, is already a demonstration of the power and complexity of the cosmos. The theoretical physicist Kip Thorne once explained that true all lies not in the imagined, but in the real. If we could see in detail the journey of 3I Atlas, from its origin in a distant star to its encounter with the Sun, we would understand that every fragment of matter tells a story of cosmic cataclysms, collisions, and stellar rebirths. This object, more than a threat, is a relic from the deep time of the universe. Furthermore, the study of 3I Atlas can help us improve our understanding of the distribution of interstellar matter. If its composition differs from that of solar system objects, it will mean that planetary formation processes can vary enormously between stars. This would allow us to build more precise models about how planetary systems originate and how matter evolves in the galaxy. In other words, every piece of data about 3I Atlas brings humanity closer to answering one of its oldest questions: are we truly unique? And it is precisely there that the technological hypothesis, although dismissed as reality, plays a symbolic role. It reminds us that we are still searching for signs of intelligence, not only outside but also within ourselves. The desire for contact reflects an ancestral curiosity, the need to know we are not alone, but for now the evidence points in another direction. 3I Atlas does not speak, it does not emit signals, it does not maneuver, it only travels. It is a mute witness of the cosmos, a messenger without a message, a rock laden with history that crosses our solar neighborhood before being lost again in the darkness. And perhaps in that silent journey lies its true meaning, to remind us that the universe does not need intention to be extraordinary, that the beauty of mystery lies not in what we imagine, but in what we can prove, and that every interstellar visitor is an invitation to look further, not to find life, but to better understand our own. Because if 3I Atlas teaches us anything, it is that even objects coming from unimaginable places can reveal truths about who we are and where we look when we seek answers. If there were a natural or technological intention behind the trajectory of 3I Atlas, the most logical destination within the solar system would not be Earth, but Jupiter. Even without resorting to speculative hypotheses, orbital calculations show that its path after the perihelion will bring it to a relatively close distance to the giant planet around March of next year. This fact has sparked special interest in the scientific community because it offers the opportunity to study a potentially significant interaction between an interstellar object and the most powerful gravitational field in the solar system, after the Sun. From a purely physical perspective, Jupiter is a key point in any gravitational assist maneuver. Its enormous mass, more than 300 times that of Earth, creates a gravitational well capable of altering the trajectory of any body that approaches. That is why many human space missions, like the Voyager, Pioneer, and Galileo probes, used its influence to gain speed and redirect themselves towards outer space. In terms of energy, a maneuver with Jupiter can save years of travel and an immense amount of fuel. Applying this principle to the case of 3I Atlas opens a fascinating scenario. If the object performs a slight variation in speed during its passage through the perihelion, for example, through the sublimation of gases as it is heated by the Sun, it could modify its trajectory enough to approach closer to the Jovian orbit. That small change, almost imperceptible from our perspective, would be enough for Jupiter's gravity to capture or deflect it in a new direction. This hypothesis, although completely natural, awakens the same kind of interest as the planned maneuvers of human probes. In this case, it would be nature itself executing a maneuver with cosmic precision. To understand why Jupiter would be a logical destination, one must analyze its role within the solar system. This planet not only dominates the gravitational dynamics of the environment, but it also acts as a shield for the inner worlds. Its enormous attraction deflects or captures a great portion of the asteroids and comets that could reach Earth. In a certain sense, Jupiter is the guardian of the solar system, the natural filter that maintains the stability of our cosmic neighborhood. If an interstellar object came close enough, it could become temporarily trapped in its gravitational field, becoming a passing moon before being expelled again. Similar cases have occurred with comets from the Oort cloud, which ended up in retrograde or highly elliptical orbits after passing near the gas giant. This would not necessarily mean a permanent capture, but rather an intense gravitational interaction capable of altering its course into deep space. Furthermore, Jupiter offers an unparalleled energetic advantage for any body wishing to harness its gravity. Unlike the inner planets, its mass allows for high-magnitude redirections. If 3I Atlas had an irregular structure that released gases or material upon heating, the combination of the impulse obtained at perihelion and the gravitational pull of Jupiter could drastically change its escape velocity. In simple terms, the object could use the solar system as a kind of natural catapult to accelerate its journey toward another interstellar destination. But there is an even more powerful reason to consider Jupiter as a key point: its system of moons. More than 90 natural satellites orbit around it, some of which, like Ganymede, Callisto, and Europa, contain subterranean oceans of liquid water beneath layers of ice. These worlds have been pointed out by astrobiologists as the most promising places to harbor life outside of Earth. If 3I Atlas followed a trajectory that brought it close to the Jovian system, observation instruments could record a unique opportunity to study how an interstellar object interacts with a potentially habitable environment. Jupiter, moreover, has a colossal magnetosphere. Its magnetic field extends millions of kilometers into space, making it a natural laboratory for studying how cosmic radiation affects bodies that come from outside the solar system. If 3I Atlas passes within that region, telescopes could detect changes in its surface composition or in the emission of particles, providing data about its internal structure. In terms of a logical destination, Jupiter meets all the criteria. It is aligned with the exit route of 3I Atlas. It possesses a gravitational attraction capable of altering its course, and it harbors moons with conditions that interest both planetary scientists and astrobiologists. Even if the object performs no intentional maneuver, nature itself seems to have charted a route that brings it near one of the most intriguing places in the solar system. To better understand this scenario, numerical models from the Jet Propulsion Laboratory have simulated different possible trajectories depending on small variations in speed at perihelion. The results indicate that a minimal change on the order of 0.5 meters per second could alter its exit angle and lead it to a close flyby of Jupiter between March and April of the following year. Although the probability is low, the mere fact that the scenario is plausible is enough to keep observation teams on alert. If this encounter were to occur, it would be the first time in history that an interstellar object gravitationally interacts with a giant planet under direct observation. This would allow for the analysis, with unprecedented detail, of the effects of Jovian attraction on an interstellar body, its acceleration, rotation, and possible fragmentation. Furthermore, it would open a window to dynamic processes that can only be modeled theoretically. The scientific potential of such a close approach is immense. The instruments of the James Webb Space Telescope, along with the ongoing missions Juno and JUICE, Jupiter Icy Moons Explorer, could coordinate simultaneous observations. While Juno analyzes the planet's atmosphere and magnetic field, the JWST could record the thermal and spectral evolution of 3I Atlas as it traverses the region. That combination of perspectives would offer a three-dimensional view of a phenomenon never before observed. Beyond the scientific value, there is something poetic in imagining an interstellar visitor passing by the giant of the solar system. From a cosmic point of view, Jupiter represents a node of gravitational power, a place where the forces that maintain planetary order converge. For an object from another star to cross that boundary would be, in a way, an encounter between two worlds, one that was born here and one that comes from the galactic abyss. And although there is no intention or purpose in that crossing, its symbolic value is enormous. Jupiter, with its immense magnetism and its court of icy moons, has for centuries been the stage for human dreams about cosmic expansion. For an interstellar messenger to pass so close reminds us that the universe is in constant motion, that the boundaries between stellar systems are permeable, and that what seems impossible today may become the object of real study tomorrow. The coming months will be crucial. Observatories will continue monitoring any variation in the speed of 3I Atlas after perihelion, attempting to determine if its course adjusts towards the Jovian region. A minimal deviation will be enough to confirm that something, a natural force, an ejection of material, or simply the mechanics of the cosmos, has directed it towards the largest planet in our neighborhood. And if that occurs, the story of 3I Atlas will not only be that of the third detected interstellar object, but that of a traveler which, after crossing the space between stars, grazed the domain of the gaseous colossus that reigns over our solar system. If 3I Atlas, after its passage through perihelion, were to head towards the domain of Jupiter, the moons of the gas giant would be the most interesting natural targets, at least from a scientific and energetic point of view. Within the inner solar system, there is no collection of bodies as diverse and potentially habitable as the Galilean moons, Io, Europa, Ganymede, and Callisto. Each of them represents a unique microcosm with geological, chemical, and magnetic characteristics that make them natural laboratories for the study of life and planetary evolution. To understand why these moons are so attractive, one must observe how they interact with Jupiter. The planet's powerful gravity generates tidal forces that stretch and compress their interiors. In the case of Europa, this process heats its core enough to maintain a global ocean beneath an ice layer approximately 15 kilometers thick. The visible fractures on its icy surface are direct evidence of this internal dynamics. Missions like Galileo and Europa Clipper have detected indications of organic compounds and salts in the plumes that emerge from the crust, suggesting cryovolcanic activity, that is, jets of saltwater expelled into space. Ganymede, the largest moon in the solar system, is even more impressive. Its size exceeds that of the planet Mercury, and it possesses something that no other known satellite has: its own magnetic field. This magnetism makes it a special environment within the already complex field of Jupiter, generating auroras and regions of partial protection against radiation. Its subsurface harbors a vast stratified ocean formed by multiple layers of ice and liquid water, possibly with dissolved minerals. In theoretical terms, that ocean could serve as a natural source of resources for any human or robotic mission wishing to establish a base in the Jovian system. For its part, Callisto presents itself as a different, but equally relevant, option. Its surface is covered by ancient craters that have remained intact for billions of years, indicating minimal geological activity. However, measurements of Jupiter's magnetic field suggest that beneath that inert crust, a salty ocean might also exist. Callisto has a crucial advantage: its distance from the most intense zones of Jovian radiation. While Europa and Ganymede constantly face the bombardment of charged particles trapped in Jupiter's magnetosphere, Callisto remains in a safer and more stable region, making it the ideal place to establish a permanent base for an eventual human or technological presence. If an interstellar object like 3I Atlas followed a course that brought it close to the Jovian system, these moons would be the natural settings of its final destination. From an energetic point of view, they are points of equilibrium, large bodies with sufficient gravity to attract material, but without the destructive intensity of Jupiter itself. Furthermore, their icy composition offers physical advantages that cannot be ignored. Water ices, upon sublimating, release vapor that can act as a natural propellant, allowing for small trajectory adjustments without the need for artificial energy. For astronomers, observing the interaction between 3I Atlas and the Jovian environment would be like witnessing a cosmic experiment in real time. If the object passed near these moons, instruments could record thermal variations, surface fragmentations, and even potential transfers of material between bodies. It would be a unique opportunity to study panspermia, the hypothesis that proposes life can travel between worlds attached to rocky fragments or interstellar ice. Furthermore, the subterranean oceans of these moons offer ideal conditions for preserving organic compounds that could arrive from outer space. In theory, if fragments of 3I Atlas impacted their surfaces, part of its material could become trapped beneath the ice, preserved for millions of years. In the future, when the Europa Clipper and JUICE missions analyze these worlds with greater precision, they might find chemical traces that tell a story of interplanetary exchange. Another reason these moons are considered strategic destinations is their low gravity. For example, the surface gravity of Ganymede is only 15% of Earth's. This means that launching objects or taking off from its surface would require a fraction of the energy needed on Earth. From the point of view of space exploration, these places are natural platforms for future missions beyond the solar system. If an advanced civilization wanted to establish a base in the Jovian system, Ganymede or Callisto would be the most logical places, rich in water, relatively stable, and energetically efficient. Space engineers have already considered these scenarios in human exploration plans. NASA and ESA have discussed the possibility of using local resources like water to produce hydrogen and oxygen fuel through electrolysis. In a hypothetical future, a base on Ganymede could function as an interplanetary supply station. In that way, travels beyond Saturn or towards interstellar space would be much more feasible. In this context, imagining an interstellar object approaching that environment is not just an exercise in curiosity, but also a real scientific opportunity. Current simulation models suggest that if 3I Atlas maintains its current speed and trajectory, its closest passage could be situated a few million kilometers from the giant planet, close enough to be influenced, but not captured. If its direction changes slightly during perihelion, it could enter a closer flyby trajectory, allowing the Juno or JUICE probes to detect perturbations in the magnetic field or in the density of the surrounding plasma. In any case, the Jovian system is shaping up to be the most plausible setting for the next chapter of this interstellar journey. There, the essential elements that define modern exploration converge: water, energy, magnetism, and mystery. Each of the moons represents a different page of cosmic history, and a visitor like 3I Atlas could add a new paragraph to that story. And although there is no evidence that the object is heading towards Jupiter deliberately, the mere possibility of an interaction between both systems, one local, the other foreign, awakens a kind of fascination that transcends science. It reminds us that the cosmos is dynamic, that the paths of worlds can cross by pure chance, and that even a lost piece of matter among the stars can, for an instant, graze the gravitational heart of the solar system. If 3I Atlas truly passes close to Jupiter, we will not only have witnessed an unprecedented astronomical phenomenon, but also a dance of natural forces that illustrates the invisible harmony of the universe. And among those forces, the icy moons of the gas giant will continue waiting, spinning in silence, perhaps as the future refuges of humanity or as the custodians of the cosmos's deepest secrets. Among all the moons of Jupiter, Ganymede stands out as the most promising scientific jewel. It is not only the largest natural satellite in the solar system, but also the only known one that possesses its own magnetic field, a trait that makes it unique among icy bodies. This internal magnetism differentiates it radically from any other world in its environment, creating a kind of protective bubble within the already powerful Jovian magnetosphere. That singularity makes it a key point in any analysis about habitability, exploration, or cosmic interaction. If 3I Atlas were to approach the Jupiter system, Ganymede would be the most logical destination from a physical, energetic, and strategic point of view. To understand why, one must observe its internal composition. Measurements from the Galileo and Juno missions reveal that Ganymede has three main layers: a metallic core, a rocky mantle, and an icy crust. Between these layers are vast internal oceans that could contain more water than all the seas of Earth combined. Studies conducted with data from the ALMA telescope suggest that the ultraviolet emissions detected in its atmosphere are caused by interactions between its magnetic field and the solar wind. That is to say, Ganymede acts like a small planet within the Jovian system with its own shield and dynamics. The fact that this moon generates its own magnetic field indicates that it still retains a partially molten core, which implies the presence of geothermal energy. That heat source, combined with the pressure exerted by Jupiter's gravitational tides, could maintain stable liquid layers for billions of years. From the perspective of astrobiology, this is crucial. An environment with liquid water, internal energy, and mineral materials is the set of basic conditions for the development of microbial life. If 3I Atlas were to pass near Jupiter and deviate towards the plane where Ganymede orbits, astronomers could study something never before observed: how an interstellar object interacts with an active planetary magnetic field. The combination of radiation from the Sun, Jovian plasma, and Ganymede's magnetism would form an extremely complex electromagnetic environment. In that scenario, the instruments of the James Webb Space Telescope and the Juno or JUICE probes could record variations in particle ionization and radio emissions, helping to understand how interstellar materials behave upon entering high-energy regions. Furthermore, Ganymede is the ideal candidate for future human colonies. Its low gravity, around 15% of Earth's, facilitates the launch of space vehicles, and its abundance of ice offers an almost inexhaustible resource for obtaining water and fuel through electrolysis. But the most decisive advantage is its magnetic field, which offers some protection against radiation, a characteristic absent in most moons and asteroids of the outer solar system. This natural shield considerably reduces the biological risk for potential human or robotic settlements. In theory, if an advanced civilization, human or otherwise, sought to establish a foothold in the solar system, Ganymede would be one of the most efficient options. It possesses an abundance of resources, access to solar energy reflected by Jupiter, and is in a relatively stable orbit. From there, it would be possible to exploit the Trojan asteroids located at Jupiter's gravitational equilibrium points, which are rich in metals and organic compounds. This set of factors has led many scientists to call it the natural logistical center of the outer solar system. Let us now imagine the scenario from a purely scientific point of view. If 3I Atlas made a slight variation in its trajectory after perihelion, its course could bring it closer to the Jovian orbit. If that deviation were caused by a slight ejection of material, as happens with comets, the result could be a direct interaction with Ganymede's environment. Terrestrial and space telescopes could capture how its icy surface reacts to the radiation reflected from Jupiter. And if the object passes close enough, the JUICE probe's sensors could even detect particles from its tail or fragments released by sublimation. The interest in Ganymede is not limited to its magnetism. Its surface shows a mixture of ancient terrain saturated with craters and younger regions furrowed by grooves and ridges. This suggests an active geological past, perhaps driven by the same internal heat that maintains its ocean. In the deepest cracks, deposits of salts and simple organic compounds could be hidden, the same ones that might be found in primitive meteorites from the solar system. If 3I Atlas approached and left some material trace, that contact, although minuscule, could offer clues about the exchange of matter between stellar systems. From a dynamic point of view, Ganymede is also an ideal body for studying how magnetic fields affect the stability of objects in transit. Its magnetosphere interacts directly with Jupiter's plasma, generating gigantic electrical currents known as Birkeland currents. If a metallic body like 3I Atlas, which contains silicates and metals, passed through those regions, currents would be induced on its surface. These currents could momentarily alter its rotation or produce detectable radio emissions, offering a unique opportunity to study the physics of electromagnetic induction on astronomical scales. On a symbolic level, Ganymede also represents something profoundly human, the promise of a future beyond Earth. From Galileo's first observations in 1610 to the modern images sent by Juno, this moon has been synonymous with discovery. It is a reminder that even in the confines of the solar system, where sunlight is faint and cold dominates, there can be places full of potential. That is why, every time a possible interaction of 3I Atlas with Jupiter is mentioned, astronomers turn their gaze to Ganymede. There, the most valuable evidence about how interstellar materials behave in environments with complex magnetic fields could be recorded. In fact, the European Space Agency's JUICE mission, launched in 2023, has as its main objective to study Ganymede, Europa, and Callisto with instruments capable of penetrating the icy layers using radar and spectrometry. If 3I Atlas approaches the Jovian region during this mission's operational window, humanity could obtain a double historic opportunity, to observe an interstellar object and a giant planet in the same scientific campaign. The probabilities are small, but the mere fact that the event is possible already motivates an unprecedented international coordination. Ultimately, Ganymede synthesizes all the elements that make the Jovian system a cosmic laboratory. Its magnetism, its oceans, its stability, and its location make it a point of convergence between astrophysics, planetary geology, and biology. If 3I Atlas passes nearby, we will not only learn more about its composition or trajectory, but about the very balance of the solar system. Every particle of dust detached from the interstellar visitor could provide a key to understanding how worlds influence each other in the vastness of space. And if that encounter does not occur, Ganymede's value will remain intact. Its role as the magnetic heart of the Jovian system will continue to inspire missions, theories, and dreams. Because in the end, every time we observe an interstellar visitor passing by the planets, what we are truly seeking is not a message or a threat, but a silent confirmation that the universe is still alive in motion, connecting stories that cross for an instant before continuing their eternal journey. After analyzing its approach to the Sun, its trajectory towards Jupiter, and the potential interactions with the moons of the Jovian system, an inevitable question arises: where does 3I Atlas truly come from? This question seeks not only a point of spatial origin but also a temporal one. Knowing its origin is essentially deciphering how many millions of years it has been traveling in the void, how many stars it has crossed, and what chemical stories it carries on its surface. The most recent orbital studies conducted by NASA's Jet Propulsion Laboratory and by the Arecibo Observatory before its collapse suggest that the entry vector of 3I Atlas comes from the galactic sector where Barnard star is located, a red dwarf situated just 5.9 light-years from the Sun. This fact is significant because Barnard star is one of the closest neighbors to our solar system and is also known for having an extremely high velocity of movement within the galaxy. This means that objects expelled from its system could acquire trajectories fast enough to reach interstellar space. If it is confirmed that 3I Atlas originated in that environment, we would be looking at a physical fragment from one of the oldest and most solitary stars in our galactic neighborhood. Barnard star is a Type M4 red dwarf over 10 billion years old, more than twice the age of the Sun. It is an old, calm, and stable star, but its system could have been dynamic in the past. Theoretical models suggest that billions of years ago, collisions between planets or asteroids within its habitable zone could have generated fragments that were expelled into space. One of them, after wandering for eons, could be precisely the one we now call 3I Atlas. Computational simulations of the object's retrograde trajectory show that its direction of entry is compatible with a journey originating from that region of the sky, although an absolute connection cannot be established because galactic forces, like the rotation of the spiral arm and gravitational perturbations from other stars, alter trajectories over the long term. The coincidences are astonishing. In galactic coordinates, the entry angle of 3I Atlas coincides with the proper motion of Barnard star within a margin of error of just 2 degrees. This means that with high probability, both share a common origin in the same stellar neighborhood. If this link is confirmed, 3I Atlas would be the first interstellar object whose provenance can be traced back to a specific star. For astronomers, this would represent a milestone, a tangible fragment from another nearby solar system that has traveled to us. Spectroscopic analysis of its surface also supports this possibility. Observations from the Subaru telescope in Hawaii and the Very Large Telescope in Chile detected a spectral signature dominated by metallic silicates and iron compounds, but with an isotopic ratio slightly different from that of asteroids in the solar system. That difference suggests a formation environment with a lower abundance of heavy elements, a characteristic consistent with older systems like that of Barnard star. In astronomical terms, 3I Atlas would be a fossil witness of the birth of the first generations of planetary systems in the galaxy. If its chemical composition differs from that of solar system bodies, scientists will be able to compare both and understand how metallicity, the amount of elements heavier than hydrogen and helium, influences the formation of planets and asteroids. In a way, this object is a time capsule, a piece of the galactic past that has traveled for millions or perhaps billions of years before crossing paths with our star. Its current speed, more than 90 kilometers per second relative to the Sun, confirms its interstellar origin. At that speed, no body gravitationally bound to the solar system could sustain a closed orbit. It is an open, hyperbolic trajectory that will lead it to definitively leave the solar system within a few months. The fascinating thing is that by projecting its course backward, astronomers discover that its direction coincides almost exactly with the stellar stream of Barnard star, a kind of river of matter that moves with it through the galaxy. If this is true, 3I Atlas would have been expelled at least 1 million years ago, possibly during a planetesimal collision or by a close gravitational interaction with a massive planet. It likely spent millennia traversing dark regions of the interstellar medium, where cosmic radiation and micrometeorite impacts slowly modified its surface. That spatial erosion, called interstellar weathering, leaves a reddish patina and reduces the albedo, or capacity to reflect light. This effect was also observed in Comet Borisov, the second detected interstellar visitor, confirming that long journeys between stars alter the surface chemistry of these bodies. Astronomers have also identified an interesting visual coincidence. From Earth, the apparent entry point of 3I Atlas is located near the constellation Ophiuchus, just north of the celestial trajectory of Barnard star. On observation nights, it is possible to see both points, the star and the object, aligned in the sky. This coincidence has been poetically called by some researchers the line of stellar return, a way of expressing that the visitor and its possible parent star cross paths again, although separated by light years. If this connection is confirmed, the significance would be profound. We would not only be studying a body from another solar system, but a physical piece from the environment of a neighboring star that is now passing through ours. It would be like receiving a fragment from another world without the need to send an interstellar mission, and furthermore, it would allow for the direct comparison of materials from two different stellar systems, something that until recently seemed impossible. The scientific implications are enormous. The detailed study of its isotopic composition could reveal the temperature and density of the protoplanetary disk where it formed. The patterns of its metallic structure, its reflectivity, and its capacity to retain volatiles will allow deductions about whether it comes from an inner rocky zone or an outer region rich in ice. Every grain of dust detached from its surface during perihelion is a fragment of information about the chemistry of another solar system. In fact, several observatories have designed campaigns to capture the remnants of material ejected by 3I Atlas during its passage. NASA's and the European Space Agency's micrometeoroid detectors will monitor the entry of particles into Earth's atmosphere, seeking compositional matches. Although the probability is minimal, an impact from a particle of interstellar origin would be an unprecedented discovery, the first physical contact with matter from another star. On a philosophical level, the fact that 3I Atlas probably comes from Barnard star also awakens a particular emotion. That star has been for over a century a symbol of cosmic mystery. It was one of the first in which astronomers searched for planets, and its proximity made it a recurring target for theories of contact or exploration. Knowing that a fragment from its system may have reached us turns that ancient curiosity into tangible reality. Thus, 3I Atlas represents not only a scientific challenge but also a link between stellar systems. It is the confirmation that matter travels, that worlds are not isolated, and that the remnants of one star can arrive millions of years later to illuminate another. In that sense, this interstellar visitor is more than a physical object. It is a galactic bridge, a reminder that the universe is not a set of separate islands, but an ocean in which everything, planets, rocks, dust, and life, can eventually meet. As 3I Atlas approaches its definitive exit from the solar system, one idea resonates among astronomers, physicists, and planetary strategists: whoever controls Jupiter controls the balance of the solar system, not in a political sense, but a physical one. Jupiter is, without a doubt, the gravitational axis that defines the structure and stability of our entire planetary neighborhood. Its mass, equivalent to more than 300 Earths, generates an influence that extends for billions of kilometers, shaping the orbital dance of asteroids, comets, and minor planets. That is why, when scientists speculate about the destiny of 3I Atlas, many agree that any interaction with the gas giant would be something like a checkmate move on the cosmic chessboard of the solar system. This expression, used by the French astrophysicist André Morel in a conference at the Paris Observatory, does not intend to suggest intention, but to highlight the physical logic behind the phenomenon. In chess, checkmate is the move that defines the game. In the cosmos, Jupiter represents that position of dominance where forces converge. If an interstellar object like 3I Atlas came close enough to interact with the Jovian gravitational field, its trajectory could be permanently altered, redirecting it towards a new route or even temporarily integrating it into the solar system. In energetic terms, Jupiter acts as a gravitational sink, a kind of invisible well that absorbs and redirects errant bodies. It is the guardian of equilibrium. Without its presence, the inner planets would have been bombarded by an immense amount of comets from the Oort cloud. Simulations conducted by Harvard Center for Planetary Dynamics demonstrate that if Jupiter disappeared, the probability of impact from large comets with Earth would increase up to 100 times. That is to say, life as we know it would not have had the opportunity to develop with stability. Therefore, some scientists consider that Jupiter is not only a planet, but a natural defense mechanism of the solar system. Its enormous gravitational attraction cleans the orbits of dangerous bodies, deflecting or capturing many of them. Every time an interstellar visitor like 3I Atlas approaches its domain, astronomers know that an invaluable opportunity is approaching, to observe how the king of the solar system exerts its power. If 3I Atlas approaches the Jovian region in March, as some models suggest, its passage could represent a unique natural experiment. We would see how Jupiter's gravity, in combination with its magnetic field, alters the trajectory, rotation, and even the structure of the visitor. In a certain sense, it would be like witnessing a duel between the wandering matter of interstellar space and the colossus that defines the order of our system. From a broader perspective, this event has strategic value for the understanding of planetary systems in general. Astronomers know that many solar systems around other stars have giant planets similar to Jupiter located in comparable positions. These configurations are crucial for determining whether the inner worlds can be stable and habitable. In other words, without a protective Jupiter, civilizations would not have the opportunity to exist for long. Therefore, understanding the dynamics of our own gas giant is to understand, in a certain way, the fundamental architecture of stellar systems. The concept of checkmate makes even more sense when analyzing Jupiter's role in the redistribution of cosmic resources. Thousands of captured asteroids and comets orbit around it, a vast reserve of raw material that could be used in the future for space exploration. The so-called Trojan asteroids, which share Jupiter's orbit at gravitational equilibrium points L4 and L5, are authentic storehouses of minerals, metals, and organic compounds. If a civilization, human or otherwise, wanted to dominate the solar system from a strategic point, it would not choose Earth or Mars, but Jupiter and its network of satellites. There, the resources, energy, and ideal position to control the gravitational routes of the entire system are found. Orbital dynamics studies indicate that an object established at Jupiter's Lagrangian points can remain stable for millions of years with minimal energy expenditure. Those points are like the safe corners of the cosmic chessboard, where the gravitational forces of the Sun and Jupiter balance perfectly. That is why the idea that 3I Atlas could cross that region, even accidentally, has captured the attention of the scientific community. It would be a unique opportunity to observe how an interstellar body behaves within a stable resonance system. The interest in Jupiter is not new. From the Pioneer missions in the 1970s to Juno and JUICE today, scientists have understood that its influence goes far beyond what is seen in the images. Jupiter acts as a gravitational regulator, distributing the angular momentum of the solar system and maintaining its structure over the long term. Even small changes in its orbit could have drastic consequences on Earth, altering the seasons or modifying the eccentricity of the global climate. In that context, the arrival of 3I Atlas can be considered a symbolic event, a reminder of how the solar system, although stable, remains dynamic and open to external influences. If the interstellar visitor manages to approach the Jovian zone of influence, its trajectory could reveal details about the three-dimensional structure of the planet's gravitational field, something that not even current missions can measure directly. The interaction between both could slightly but measurably modify the object's speed, which would allow scientists to validate large-scale gravity models with unprecedented precision. But beyond pure science, the concept of checkmate also holds a philosophical meaning. Jupiter, in its role as protector and dominator, symbolizes the balance between chaos and order. Its presence allows for the existence of life on the inner worlds, but at the same time, it embodies the destructive force capable of altering any trajectory. In that sense, 3I Atlas, a traveler from another sun, upon passing near it, represents the clash between two cosmic histories, that of the foreign visitor traversing the void and that of the immovable guardian sustaining the balance of the entire system. If we think in terms of civilization, dominating or inhabiting Jupiter's orbit would be equivalent to controlling the gravitational heart of the solar system. From there, one can efficiently access both the inner and outer worlds. That is why, in the planning of future explorations, space agencies have identified its moons, especially Ganymede and Callisto, as the ideal logistical centers for the leap into deep space. Establishing a base there would literally mean moving the frontier of humanity to the threshold of the stars. On the cosmic chessboard, each planet plays a distinct role. Earth harbors life. Mars symbolizes the future of exploration. And Jupiter represents gravitational power. But only Jupiter possesses the capacity to alter the trajectory of an interstellar visitor like 3I Atlas and redefine its path. That is why, when astronomers speak of checkmate, they refer to that point where nature shows that, even without intention, there is an order that governs chaos. And if one day humanity manages to colonize the Jovian system, it will understand that Jupiter is not just a planet, but the axis of a perfect cosmic machine. From its orbit, neighboring stars, like Barnard's star, will seem even closer. Perhaps in the future, from a base on Ganymede, a human will observe the passage of another interstellar object and remember that first visitor that crossed the solar system, leaving behind a universal lesson, that mastery of the cosmos is not achieved with force, but with balance. If Jupiter is the gravitational axis of the solar system, then the Trojan asteroids are its invisible entourage, its cosmic treasure. These bodies trapped at the L4 and L5 equilibrium points of the Jovian orbit have accompanied the gas giant for billions of years. Their arrangement is so stable that they form two enormous swarms orbiting the Sun in synchrony with Jupiter, one leading and one lagging, like guardians of a silent kingdom. From a scientific, economic, and strategic point of view, the Trojans represent one of the most valuable regions in the solar system. Astronomers have catalogued more than 12,000 Trojan asteroids. Although it is estimated that more than 1 million of them could exist with sizes larger than 1 kilometer, their composition varies. Some are rich in silicates and metals. Others contain ice, carbon, and primitive organic compounds. In other words, they are a time capsule of the solar system's origins. Studying them is to understand how the planets formed, but also to identify the natural resources that could power a future interplanetary economy. For years, NASA has recognized the importance of these regions. The Lucy mission, launched in 2021, was designed precisely to explore several of these bodies. Its objective is to analyze up close 7 asteroids, 1 in the main belt and 6 Trojans, to study their composition, density, and structure. The data obtained so far reveals that many of them contain materials identical to those that compose the primitive cores of the outer planets. Some, like the asteroid Eurybates, show evidence of ancient collisions that released carbon-rich fragments. Why do scientists consider these places so special? Because the Trojans are in stable resonance orbits. There, the gravitational forces of the Sun and Jupiter balance almost perfectly, creating islands of stability in space. An object situated at those points can remain there for millions of years without any energy expenditure. In the future, these zones could become gravitational ports for space missions, supply stations, or even automated mining colonies. If 3I Atlas, after its passage through Perihelion, adjusts its trajectory enough to cross the Jovian orbit, it could pass precisely through one of these regions. From a dynamic point of view, it is a real, though remote, possibility. And if that were to happen, telescopes could record an extraordinary event, the encounter between an interstellar object and the oldest remnants of the solar system, a visitor from another star traversing the fossil archive of our own. The scientific implications would be enormous. Analyzing how solar radiation, Jupiter's gravity, and the Trojan dust fields affect the trajectory of an interstellar body would allow for the improvement of orbital evolution models on galactic scales. Furthermore, it could offer clues about gravitational capture processes. If an object like 3I Atlas moved at the appropriate speed and angle, it could become temporarily trapped in one of those stable zones. It would be the first time that humanity would observe an interstellar capture in real time. But beyond the theoretical value, the Trojans represent a practical opportunity. Within them are concentrated the materials that could sustain a space civilization. Many contain frozen water that can be converted into fuel and minerals like nickel, iron, and platinum. In energetic terms, extracting resources there would be more efficient than doing so on more distant bodies or on the surface of planets with high gravity. That is why space agencies and private companies are looking towards these regions with growing interest. The possibility of establishing bases around Jupiter is not a distant fantasy. Electric propulsion technologies, the use of solar energy over long distances, and the local production of fuel would allow for sustained operations at the Lagrange points. From there, ships could travel to Saturn, Uranus, or interstellar space with minimal expenditure. In strategic terms, whoever manages to dominate those gravitational points will have direct access to the most abundant resources in the solar system. That is why some scientists and theorists of planetary colonization have described this region as the gold belt of the solar system, not for its color, but for its potential value. Gold, platinum, and other precious metals are byproducts of stellar fusion processes, and asteroids are their natural deposits. In the Trojans, furthermore, the low temperature preserves volatile compounds, making them intact chemical reserves since the formation of the system. From a scientific point of view, the Trojans are also fascinating because they could reveal how Jupiter moved in the early days of the solar system. Planetary migration models, especially the NICE model, indicate that the gas giant changed its orbit after its formation, dragging a large number of asteroids with it. The Trojans would be the survivors of that migration, captured bodies that preserved the traces of that primordial chaos. If 3I Atlas were to traverse them, we would be witnessing the convergence of two cosmic histories, that of the origins of the solar system and that of a traveler coming from outside it. From a more poetic perspective, the Trojans represent the frontier between the known and the unknown. They are the debris of creation, orbiting in equilibrium around the most powerful planet in the solar system. There, time seems to stand still, impacts are rare, radiation is faint, and gravity is sufficient to maintain stillness. If an interstellar visitor were to cross them, it would be as if the past and future of the cosmos touched for an instant. For humanity, that place symbolizes a promise. The first steps towards a truly spacefaring civilization will not be taken on the surface of Mars or in Earth orbits, but in regions like the Trojans. There, where the sun's energy is still usable and resources are abundant, the first self-sufficient interplanetary stations could be built. Jupiter would provide the gravitational balance, the asteroids the materials, and the nearby moons the scientific and logistical support. In that context, the presence of an interstellar object like 3I Atlas acquires a double meaning, scientific and symbolic. It is a reminder that cosmic paths cross, that the solar system is not a closed system, but part of a larger network of material and energetic exchanges. Its passage near Jupiter and the Trojans will not be just an astronomical spectacle, but an opportunity to reflect on the continuity of matter in the universe. The coming years will be decisive. When 3I Atlas completes its passage and moves away into interstellar space, the instruments will leave behind terabytes of data, spectra, light curves, simulations, and trajectory maps. In them will be recorded not only the history of an object that came from another star, but also that of the solar system that received it, because at its core, science and history are the same, the art of observing encounters. And Jupiter, with its court of moons and its army of asteroids, will remain the king of that cosmic chessboard, a king that does not need to move to dominate, because its strength is gravity and its throne is eternity. With all we know up to now, it is impossible to deny that Jupiter is the strategic heart of the solar system. If 3I Atlas, that visitor which traveled for millions of years from another stellar system, had the capacity to perform a controlled maneuver, its ideal destination would be neither the Sun nor Earth, but Jupiter itself. And not by simple coincidence, but for physical, energetic, and scientific reasons that make it the most efficient point for any civilization that wished to study, colonize, or utilize the resources of our cosmic neighborhood. Jupiter meets all the necessary conditions to transform into a natural base of operations in deep space. Its gigantic mass guarantees a powerful source of gravitational energy. Its moons, especially Ganymede, Europa, and Callisto, offer abundant water and thermal stability beneath the ice. And the Trojan asteroids orbiting around it provide minerals, metals, and organic compounds that could sustain a complete interplanetary infrastructure. From a logistical point of view, establishing oneself in Jovian orbit would be equivalent to controlling the natural corridors of matter and energy in the solar system. Scientists compare it to a galactic nexus point, a place where the most important orbital routes cross, a node of equilibrium between the Sun and the outer planets. There, the energy of the solar wind diminishes, but gravity is still strong. Cosmic radiation can be studied without the interference of Earth's magnetosphere, and the distance to the confines of the solar system is significantly reduced in terms of energy expenditure. In short, Jupiter is the natural springboard to the stars. If 3I Atlas, as some orbital dynamics models propose, were to pass close enough to the gas giant, it could utilize gravitational assistance to change its direction and accelerate its exit from the solar system. This phenomenon, known as gravity assist or the gravitational slingshot effect, is exactly the technique that human missions use to reach the outer planets. The Voyager 1 and 2, Pioneer, and New Horizons probes used this principle to gain speed without spending fuel. If an interstellar object executes a similar maneuver naturally, it would demonstrate that the very physics of the universe allows for mobility between stellar systems without the need for artificial propulsion. But the scientific interest is not limited to orbital mechanics. Jupiter also acts as a natural particle accelerator. Its magnetosphere, the most extensive in the solar system, traps protons, electrons, and high-energy particles, generating spectacular auroras and extreme conditions that can only be found near stars or black holes. Studying how an interstellar body interacts with that field could reveal secrets about the behavior of matter under intense radiation. In fact, the passage of 3I Atlas near the planet could produce a detectable variation in radio emissions or in plasma waves, something that radio telescopes are already prepared to record. The Jovian moons would be the next natural chapter of this story. Europa could show how its ice layer reacts to the arrival of an object releasing interstellar particles. Ganymede, with its magnetic field, would allow for the study of the effects of electromagnetic induction on foreign materials. And Callisto, with its relative geological calm, would serve as a fossil record of impacts and cosmic depositions. If any of these worlds were to receive fragments detached from 3I Atlas, humanity would have in its hands the first physical evidence of a direct exchange between stellar systems. From a theoretical point of view, all this falls within the so-called hypothesis of cosmic connectivity. This idea holds that the exchange of matter between stellar systems is much more frequent than previously believed. Objects like 3I Atlas would be the natural messengers of this galactic network, transporting organic compounds, minerals, and complex molecules across the frontiers of interstellar space. If part of that material reaches regions like Jupiter's moons, it could chemically enrich them or even sow the basic ingredients of life. These types of processes are, at their core, the basis of natural panspermia, a theory that proposes that the essential components of biology can disperse from one system to another via comets, asteroids, or fragments expelled by stellar explosions. In that sense, the passage of 3I Atlas near the Jovian system might not be just an astronomical event, but one more chapter in the universal history of the potential exchange of life. The most recent calculations show that after its passage through Perihelion and the environment of Jupiter, 3I Atlas will follow an ascending trajectory that will lead it to definitively abandon the plane of the ecliptic. In a few years, its brightness will fade until it becomes undetectable, even for the most powerful telescopes. But the data collected during this brief passage will remain for centuries: composition spectra, light curves, simulations of its acceleration, and comparisons with formation models of other stellar systems. In a way, humanity is witnessing something more than a scientific observation. It is witnessing a connection between solar systems, a wordless communication between stars. 3I Atlas travels without purpose, but its existence reminds us that the universe is not composed of borders, but of open paths. Every rock that crosses interstellar space carries with it the chemical signature of its parent star, like an encrypted message waiting to be deciphered. Jupiter, for its part, acts as the great receiver of those messages. Its immense gravity collects what the cosmos throws, storing fragments of foreign histories in its system of moons and asteroids. In it, time and matter intertwine to form the largest archive in the solar system. In this dance of forces, every passing object leaves its mark, and every mark expands humanity's understanding of the universe. That is why astronomers call this event the perfect move, not because there is intention, but because all the pieces of the cosmos seem to align in a movement of mathematical precision: an object from another star, a colossal planet capable of altering trajectories, and a network of moons and asteroids that serve as silent witnesses to that encounter. Everything happens at the exact moment, in the exact place, before the eyes of a civilization that is just beginning to understand its position on the galactic chessboard. 3I Atlas leaves us with a powerful lesson. It does not matter if it comes from Barnard's star or from another corner of space. Its passage demonstrates to us that the universe is dynamic, that matter travels, transforms, and intersects. Jupiter, with its majestic gravitational field, is the point where those trajectories meet, where the paths of the cosmos curve and cross. Thus, the checkmate move of the solar system is not an event of domination, but of equilibrium. The perfect move is not one that destroys, but one that connects. In the vastness of space, where most worlds remain unknown to each other, the encounter between 3I Atlas and Jupiter is a symphony of gravitational precision, a natural masterpiece that demonstrates that order and harmony exist even in the apparent chaos of the universe. And when this visitor is finally lost among the stars, the telescopes will fall silent, but the memory of its passage will persist. In every piece of data, in every analysis, in every simulation, humanity will preserve the echo of a wordless message, that the cosmos is not empty, but full of improbable encounters, of stories that cross only once to remind us that even in the solitude of space, everything is connected.